So, next we are going to discuss then how to determine the external quality factor and the coupling coefficient by using full wave simulator. So, what is the importance of this work, that let us say you have calculated some external quality factor, now you need to implement the filter, but then what should be the physical dimension of the filter. So, what we do, we first do a parametric study for a given resonator and then plot the variation of Q external versus some parameter. Then once we have that requirement, so we need this particular Q external, then from that previous variation what already we plotted, from that we find out the values. Similarly, for the coupling coefficient, we first do a parametric study by using full wave simulator and plot the coupling coefficient versus, let us say, gap between two resonators. Once we have that plot, then you calculate your matrix, and the matrix, from the matrix element you now the required values, from the required values you choose the gaps which you already have from the plot. So, we will start with the determination of QE. You see, we are here showing as an example to microstrip resonators. It is called open loop resonator. It can be even one straight lambda g by 2 resonator also. Now, we can directly connect feed line to this resonator as shown in this first figure, and in the second figure it is coupled by a gap. So, electromagnetic power, it is coupled to the resonator through this gap. It can be coupled via electric field or magnetic field. Now, if we change the feed point in the first design, then accordingly the external quality factor will change, or you can say in other words, power lost from the resonator into feed network, it will change. So, it is a function of this separation T. Similarly, in the second case, Q external, it is a function of this gap G between the feed line and the resonator. Now, if I increase this gap, in that case what I expect, that power coupled from resonator to feed line, or better to say power lost into feed line, it will decrease with increasing gap, or in other words, then Q external will increase. So, Q external, it decreases with the smaller gap value. Now, how to calculate it? Simply we draw this structure in any full wave simulator and then plot the S11, mainly its phase of S11. So, here one example is shown here. The phase of S11, it is a function of frequency. So, if I place my input port exactly at this point where this coupling start, then it crosses 0 at the resonance frequency, but practically it is not. So, there always will be a shift. So, what you have to do, you have to first find out the resonance frequency of this resonator and note down what is the phase of S11 at that particular frequency, then go left hand side minus plus 90 and right hand side minus 90, and note down these two frequencies represented by delta omega minus and delta omega plus. From that we have the delta omega plus minus 90 degree bandwidth, and Q external, it simply then omega naught divided by delta omega plus minus 90 degree. Now, if you can calculate input impedance as seen by your feed line, then we can also calculate the Q external mathematically. It is equal to RL into omega naught by 2 into del omega of B at omega naught. But for the first structure, we can directly calculate the input impedance, because from this input point you can see it looks like two open stub, one open stub on top, one open stub bottom, and they are in parallel at this feed point. So, we can easily calculate then what is the input impedance seen by the feed line, and we can calculate the external quality factor for the first example. But for the second example, it involves a gap, and it is really difficult to represent a gap mathematically. It can be done, but the procedure is complicated. So, it is better to calculate the Q external by using a full wave simulator. Now, what we do? We calculate Q external for different gap. Let us say you starts from g equal to 0.05 millimeter, then at a step you change it to g equal to 5 millimeter. For each and every steps you calculate what is the Q external value and plot it with g. Now, once you have the requirements Q E 1 and Q E n, now already you have the plot, then from the plot you choose the gap value. So, how to determine the resonance frequency? So, at resonance frequency, power is coupled from feed line to resonator. If I plot magnitude of S11, we will be expecting one dip in S11, but sometimes that dip of S11 it is influenced by other parameters, the feed length and other things. So, it is suggested to observe the group delay plot and find out where delay is maximum, that will give you the resonance frequency. So, what we are doing here, we are simply calculating the group delay of S11, del omega of angle of S11 and plot it versus frequency, and it is maximum at the resonance frequency. So, from the maximum point you note down what is the resonance frequency. Then once you have the resonance frequency, you note down what is the phase value at resonance frequency. Let us say it is 10 degree, plus 10 degree. Then you go left hand side plus 90, so plus 100 degree, where right hand side minus 90, so where minus 80 degree. Note down these two frequencies, and then you have delta omega plus minus 90, calculate Q external. Now, coupling. How to determine the coupling coefficient? Before that, let me discuss about different types of coupling. Again, I am giving you a microstrip line example. Even at millimeter wave frequencies, we can use microstrip line to some extent. So, this one again we are showing open loop resonator, and these gaps they are facing each other. In this case, energy is transferred from one resonator to another resonator by fringing electric fields, and we call it electrically coupled resonator systems. In equivalent circuit, then this coupling, it is, since it is through electric field, we can represent it by capacitor. So, in this figure you can see one isolated resonator, it is represented by L1 C1, but for this coupled system, let us say we have a capacitor connected between two resonators which represents the coupling, it is given by Cm, and since we are representing it into two symmetrical parts, we are representing it by twice Cm, and C1 it becomes C1 minus Cm, and in this case this coupled system it will have two frequencies. So, one single resonance frequency, it will split into two components, omega 1 and omega 2. It can be given by this expression, one is due to plus Cm, another one due to minus Cm. Now, how to determine this coupling coefficient? By using any full wave simulator. So, you see we are using the same coupled open loop resonator, but we have to excite the resonator to obtain the S21. We can determine the coupling coefficient from S21 plot. We are using one port 1 with a feed line, port 2 with another feed line, and we are using gap coupling. Now, these resonators, it should be isolated from rest of the world for this coupling coefficient calculation, but without these feed lines we can't excite the resonators. So, practically what we do, we use a large gap here and we assume that they are loosely coupled, or we use loosely coupled feed lines, and these feed lines do not affect the resonance condition of this coupled system. So, in that case, if I plot S21, whatever we obtained from any full wave simulation, you can see the plot here, magnitude of S21 in dB versus frequency. We have two peaks. These two peaks represent now that two resonance frequencies of these coupled systems. Let us say the second one is F2, the first one is F1. Then coupling coefficient K, this is equal to F2 square minus F1 squared divided by F2 squared plus F1 squared. Now, between these two peaks at one resonance frequency, this coupling, it will be electric coupling, and at another resonance frequency, the coupling, it will be magnetic coupling. For electric coupling case, this lower resonance frequency, here actually we have electric coupling, and at higher resonance frequency we have magnetic coupling. Okay, so what is electric coupling, what is magnetic coupling? Let me discuss a little more before. We know the coupled microstrip line, already we discussed in even odd mode theory analysis. When they are excited in same field with zero phase difference. So, this is the electric field plots just below the strip. You can see the vector electric field, they are in same direction. So, there is no phase difference between two EM signals. And now, if I consider one plane in between these two strips, what is the orientation of electric field on this mid plane? This is parallel. That means, we can place one open circuit plane or one PMC here, and we call it FM or magnetic coupling, because we know there is no electric field penetration from left hand to right hand side. We call it even mode excitation or magnetic coupling. And right hand side now, the same coupled microstrip line, but now we are exciting it in odd mode condition. So, left hand side you see electric field, it is from bottom to top, and right hand side it is top to bottom, and because of that we have some fringing electric fields in between coming from right to left. And now, on the mid plane, which is symmetrically placed between these two strips, electric field, it is exactly perpendicular, or this plane you can call it a shorting plane or PEC, electrically perfectly electrical conductor plane. And now, it is clear that this coupling is due to electric field, we call it electric coupling. Similar situation also exists in waveguide technology. For this particular example, I am showing actually SIW. We have two cavities, they are coupled to each other through one window, iris. So, this chain of vias, they represent short wall, and inside we have dielectric. So, it is a dielectric cavity bounded by PEC all around, and between two cavities we have a small opening. So, power is coupled from cavity 1 to cavity 2 through this opening. And now, you see in this left figure, look at the orientation of electric field, they are in same direction. So, on this mid plane again we have even mode like situation, right. So, we can place one PMC and we call it magnetic coupling, and in right hand side figure look at the electric field orientation. In cavity 1 it is bottom to top, and in cavity 2 it is top to bottom. So, the orientation of electric field is different, and if I consider a symmetrical plane in between, it can be shown the electric field direction is perpendicular on that, and it behaves like a PEC, and it is electric coupling. So, for a coupled resonator system, so we have two frequencies. If at lower frequency it is electric coupling, this coupling is due to electric field, we call it electric coupling, and if the lower frequency it is due to magnetic field, then we call it simply magnetic coupling. So, for open loop resonator, You see, if we just change the orientation of open loop resonator, then it becomes magnetic coupling. We can also analyze this structure. You see, at open end, so at resonance frequency, length of this open loop, it is lambda g by 2. At this open ends, we have electric field maxima, current minima, and at the mid plane we have current maxima, electric field minima. So obviously the coupling where current maxima, electric field minima, we don't expect any electric field coupling, and it should be due to magnetic field. And for this magnetic coupling, what we do, we represent in equivalent circuit this coupling by a mutual inductance Lm, and this is the equivalent circuit. So exactly same procedure to calculate K, simulate this structure. Remember to take loose coupling for this feed line to resonator coupling, and then you simply plot S21. Once you have F21, F1, calculate the coupling coefficient from this formula. In coupling matrix, we represent Ke and Km with different signs. So if Ke is positive, for example, Km usually we represent by negative number. Sometimes we may face mixed coupling. So the coupling is, let us say for this example, it is due to both electric field and magnetic field. And sometimes what happen, for some given gap, let us say, not for this example, I have some other example, yeah, this one. So right hand side figure, you see one interesting thing, we are plotting coupling coefficient for different separation or gap between two resonators. So here it is being changed from, let us say, 0.2, 0.3 millimeter to 3 millimeter, and for each and every separation we are calculating K from Coulomb simulation by noting down F21 and F1 and then plotting it. Now it is interesting to see that first coupling coefficient it decreases at some given value, let us say for this particular example 0.9 or 0.95, it is becoming 0 and then again increasing. It is due to the opposite behavior of Ke and Km. So at this 0.9 or 0.95 millimeter, Ke and Km they cancel each other's effect, and at lower frequency it is electrical coupling, at higher frequency it is magnetic coupling. And for this left hand side figure, it is always mixed coupling, and the coupling coefficient, you see, it decreases with increasing separation. Now once you have this plot, so in the synthesis step, if we go back, you see we will be having different Mij values, that nothing but coupling coefficient between different resonators. So you can then calculate what is the gap required between two resonators for the required coupling coefficient from this matrix. Now I will show you some example of overcoupling and undercoupling case. So we are considering a simple two resonator filter system. This is the input feed line, this is the output feed lines, and in between we have two resonators, and from this configuration you can see we are using electric coupling. Now coupling coefficient is determined by gap between two resonators, and the external quality factor, it is determined by the gap between feed line and the resonator. Now we may have, depending on the Q, E and K values for a given system, we may have three different scenario. One case 1, we call it overcoupled condition, when K is greater than 1 by Q E plus 1 by Q UL, where QE this is the external quality factor and Q UL this is the unloaded quality factor of the resonator, and in the second case we call it undercoupled case when K is less than this value. So, you see this is a typical situation, overcoupled scenario. This red line it shows the S21 plot. So, from this the coupling K it is more than the required 1 by QE, or you can say this is the input matching and output matching for this response is really poor, and S11 in between these two frequencies it goes up and touches 0 dB. So, to bring it down, what we have to do, we have to decrease QE value, or we have to decrease further this gap, fitting gap, and then only you can take it up, this S21 take it up, and input matching can be improved. In the second example, this is overcoupled scenario, sorry, this is undercoupled scenario. So, where we are using too small gap for the feed lines, that means QE is smaller than the required value, and coupling coefficient then we have to increase, or the coupling gap we have to increase to obtain a higher S21 at the midband. And the third case, when we have critically coupled scenario, in this case actually K is equal to this 1 by QE plus 1 by QUL, and you can see two resonances they becomes now one resonance, they merge. So, in practical situation what we prefer, it should be little overcoupled. So, this is one example. This is one 5-pole filter response using hairpin resonators, and this is the simulated response without considering any loss. So, that means considering PEC and loss tangent equal to 0. So, you see after optimization how the band pass filter response it looks like. Next is practical design consideration. So, we have already, let us say, so what are the steps? First step is filter synthesis. So, we have to find out the coupling matrix, required external quality factor, then the implementation scheme. Let us say already you have determined what are the gaps required between different resonators, what are the gaps required for the feed lines. Even after implementation, you will see that the response it is not coming, the desired response is far away. So, after implementation we have to do some sort of optimization. So, once you implement just by using this coupling matrix and whatever the plot you have, you are very close to final result, but it is not the final result. So, after that you have to use some sort of optimization. Now, for practical implementation you have to consider many other points. For example, while you are fabricating the filter structure, you always have some tolerance. So, you let us say you want a gap of 0.12 millimeter, but your PCB fabrication process it may not support that accuracy. It can be anything between let us say 0.1 to 0.15 millimeter. So, an error of 0.03 millimeter. So, because of that error your passband response will deteriorate. So, in your simulation you have to consider this all these worst condition cases, and then find out even after that your filter is working or not. So, in this example whatever I have shown till now all based in microstrip line technology. Then when we should use microstrip line, or when we should use rectangular waveguide or NRD or dielectric resonator, how to determine those factors. So, they are determined from size requirements, power handling capability, power handling requirements. For example, let us say we have to design a filter for radar transmitter applications, where the power level can be as high as 1 kilowatt. Obviously, we can't use microstrip line, we have to go for a rectangular waveguide. Another example, let us say we need a very narrow bandwidth at millimeter wave frequency. Let us say just we need 0.5 or 500 megahertz bandwidth filter at 60 gigahertz. We can't design that in microstrip line technology, because filter loss, passband loss, it depends on unloaded quality factor resonator as well as the fractional bandwidth of the filter. So, we have actually relationships, I will show you later, and many other factors like asymmetrical skirt selectivity. So, it happens due to the difference in even and odd mode velocities. The left hand side and right hand side roll up, they are different, attenuation rates are different. So, you have to be careful about that, otherwise we have to use some sort of minimization technique that will give you almost symmetrical response. Then next, in filter theory we did not consider the higher harmonics. What about the higher harmonics? It can appear just next to passband, and packaging issues finally. So, we have to use some sort of shielding or packaging finally, and that should not affect the filter performance. So, the challenges: higher bandwidth needs higher coupling, close spacing. One way, instead of using side by side resonator, we can use actually broadside coupling to have higher coupling value. And then fabrication tolerance, already we discussed, because if the gap it changes due to fabrication tolerance, then coupling coefficient it changes, and if the coupling coefficient changes, then the bandwidth and everything changes. So, similarly, stop band rejection level, it also depends on fabrication tolerance. And now passband loss, it increases with decreasing fractional bandwidth and decreasing QUL, unloaded quality factor. We have a closed form expression for that. Delta L naught midband loss, this is approximately 4.343 summation I equal to 1 to n, n is the order of the filter, and omega c divided by FBW into QUL into GI in dB. So, it depends on fractional bandwidth, obviously order of the filter, and the unloaded quality factor. So, if the stored energy inside the resonator it decreases, or in other words, if the loss from your resonator it increases, then we have lower unloaded quality factor, it will give you high loss. Not only that, if you increase number of resonators to obtain higher attenuation, you have to increase number of resonators. So, in that case again loss will increase. And another important parameter sometimes we forget, it also depends on fractional bandwidth. For the same resonator, if you are asked to design a filter with a fractional bandwidth of 1%, and somebody else, let us say using the same resonator to design a filter of fractional bandwidth 10%, you will be facing more loss, your FBW is just 1%. So, sometimes its value it's so negative that you simply can't use microstrip line at millimeter wave frequencies because of this increased loss due to smaller FBW requirement. Okay, so now we will take a break. After that we will start other passive components. Thank you.